Welcome, students, to Chapter 9 and beginning of functions of several variables. And we're talking about vector calculus. So Chapter 9 now is the second part of this course. And we're starting with 9.1 functions of several variables. In this section, we combine the concepts of parametric curves with vector functions. So let's start the marathon. Let's suppose, guys, that we have here a curve. This is our curve C. As you see, this is the blue one here. We can define this curve by anyway as y equal f of x. This is what we call the standard presentation of any curve. Like, for example, when I say y is equal x squared, what's this? What's the graph of this curve? This is the graph of the curve. It's y equal x squared. So now we have what we call the standard function curve. So this is presented as y equal x squared. This is the standard presentation of this curve. Let's take any point on the curve, which is the point x and y. Here's the given point, taken point on the curve. Let's define it as x and y. We can parameterize this curve, and we call it parametric curve, if I can replace and redefine x as a function of t. So I'm going to let x equal x of t, or x equal any f of t, and y to be what? Y of t, which means y equal g of t. Could be g of t or y, it doesn't matter. If I change these 2 points, x and y, to functions of t, then in this case, we call this curve what? Parametric curve. We parameterized it as functions. What is this going to lead to, by the way? When I change xy, notice here that the point xy is fixed, is not moving, because it's like 2, 3, whatever it is. If I redefine it as x of t and y of t, what is this going to happen? With the time t, x and y are going to start changing, isn't it? And when they change, what's going to happen? This point is going to start moving on the curve. And this will make it what? A parametric curve. So which means now the point here that was fixed point now started moving on this curve, and this is called the parametric curve. So if I redefine the point xy as functions of x of t and y of t, then what have we done? We defined, actually, we parameterized the curve C to something that is well defined and can be graphed. Don't forget that x of t and y of t must be continuous functions on some interval a and b. All right, so this is a kind of parameterizing of a function. If we are in 3-dimensional space, you know, a point, here's our curve again, C. This is C. And by the way, here, the standard form of this one is Z equal f of xy. If you are in 3-dimensional space, then Z is equal to what? F of xy. So this is the standard presentation of a function in 3-dimensional space. Now I'm going to parameterize it. How? I'm going to take a point on the curve like x, y, and z. We will represent x and x of t, y as y of t, and z as z of t. In this case, if I do that, then what did I do? I just parameterized the curve and change it to a parametric curve. Now, let's take the point that was on the curve again, which is x and y in 2-dimensional space. And let's suppose I parameterize the point and the curve with x of t and y of t. Let's take the vector, guys, the red vector that starts from the origin, goes all the way to the point, the red vector that you see here. If you leave it as x and y, then we can call this vector actually r, we can call it r, equal x I plus yj, or I can call it as x and y. We can call it like this. So this is now a vector. Now r is a vector, but this is what? Just a vector. If I replace x with x of t and y by y of t, so what's going to happen now? This is what we call a vector valued function. This vector now is not just a vector, it's called a vector function. Clear? So now we are redefining our curve C by parameterizing it with x of t and y of t. Then I'm going to take the vector that starts from the origin and ends at the point x and y, which can be also x of t and y of t. In this case, what have we done? We usually call this R as a vector, right? From 0, 0 to x and y. But if I change x and y to functions x of t and y of t, so this is having a new name. This vector is not going to be called only vector, but it's going to call what? A vector valued function. Alrighty. If we are in three-dimensional space, it's the same thing. R of t will be f of t, g of t, h of t, or it could be what? F of t I, g of t j, and h of t k. So this is what we call a vector valued function. So what did we do? We redefined the curve from being standard curve to what? To vector curve. I will give you an example on that one. Let's take this, guys. Find the vector function of the function f of x equal x squared. This is a standard function. Now we have y equal x squared. You know the graph of this one? This is our curve. This is y equal x squared. This is the standard presentation of this curve. So it's not parameterized yet. How can I parameterize it? Since I am in two-dimensional space, x and y, I will let here, don't forget, okay, let r of t is what? Is x of t I plus y of tj. I'm going to change any point on the curve, and this is what we call the vector function. This is the vector valued function. All right, guys. So how do I change this to that? I'm going to go back to my y equal x squared. The easiest way to represent it from functions or standard function to vector function, we do the following. Let x of t equal to t, guys. I'm going to let x of t equal to t. So this implies, what do we know about y? Y is equal to what? X squared, isn't it? So, but x here, I took it to be t. So in this case, y is going to be what? T squared. So if x is t or x of t is t, then we can say, or here, we can say y of t is going to be x of t squared, which is equal to t squared. Therefore, r of t is going to be x here, I call it t, so this is ti plus t squared j, where x of t here is t and y of t is t squared. So what is this? I moved it from the standard form to the what? To the vector form, vector valued function. What if it was backwards? What if r of t is equal to ti plus t squared j? So put it in the standard form. What do you do here? First, okay, this is a vector function. I can say find the standard function. This is a vector function. Put it in the standard form. What do? I notice here, we know that r of t is what? Is x of t I plus y of t j. So here in the question, x of t, we can just call it x is what? Is t, and y is what? T squared. If x is t and y is t squared, so this implies from these two that we can say that y is equal what? Look at this, y is t squared, but t is x, so y is what? X squared, and you are done. So you can go always back and forth. If I give you the standard form, can you give me the parametric form? Yes, I can. If I give you the vector form, can you give me the standard form? Yes, we can. Here's an example. Find the standard function of this vector function. So now it's given in this vector function, guys. So what I'm going to look at, we know that any r of t is supposed to be x of t I plus y of tj. So what's x of t here in this case? It's sine t. What's y of t? It's that part, which is cosine t. So far, so good. This is x of t and y of t. What's the best relation I can figure between these two guys is that I'm going to square both of them. So what if I take x squared plus y squared? What do we get, guys? X squared plus y squared is sine squared t plus cosine squared t. But sine squared plus cosine squared is 1. So what do we have here? So this is equal to 1. So the equation is going to be x squared plus y squared is equal to 1. This is, guys, our equation now. You see, I changed it from vector to this form. So the standard function now is x squared plus y squared equal 1. I don't have to write it explicitly. This is an implicit presentation of the function. And we all know, what is this, by the way? This is nothing but equation. So this is the equation of a circle, isn't it? Centered at the origin with radius 1. So the graph is exactly that thing. Here it is. So what do we have? We have a circle of radius 1, which is called the unit circle. So this vector valued function represents a unit circle in xy plane. If you keep it as is, r of t, and you don't change it, if you don't change it to the standard form, you won't be able to graph it. So if I give you a function in the standard form, you can graph it. If I give it to you in the vector form, you cannot. So what should you do? You should first parameterize it, change it to the standard form, then what? Then graph it. All right, now let's talk about vector equation of a line and parametric equations of a line. You had this one before in linear algebra. Let's suppose, guys, I have this line, any line L. You know, in standard form, to find the equation of a line, the standard equation of a line, we usually do what? We need a slope and a point. But to find the vector equation of a line, I'm going now to take any point on that line. Let's take any point here. Let's call it x1, y1. It's a known, well-known point. Let's suppose now I'm giving you a line L, and there is a point on that line, which is the point x1, y1. Next is, let's suppose that you were given a vector that is parallel to the line. Let's call this vector A. In linear algebra, we used to call it the vector D. Okay, so what's this vector A, by the way? The vector A can be presented as the point A1 and A2. So this is a vector who starts at this origin and ends at A1, A2. So we're going to say, let L be a line that passes through the point x1 and y1 and parallel to the vector A, which is A1 and A2. Then the vector equation of the line L is what? I think you remember that from calculus, or let's say from calculus 2 or linear algebra, is x equal to the point x1, y1 plus t times a1 and a2. All right, this is what we call it, and this x can be presented as x and y equal to x1, y1 plus t, a1, comma, a2. This is, guys, what we call the vector equation of the line. Now, let's talk about the parametric equations of the line. How do I find the parametric equations of the line? Now look at this one. This can be completely, now this is what we call vector equation of the line. To find the parametric equations, of the line, what do we do here, guys? Let's look at it carefully. I'm going to take x and y equal to, look what I'm going to do here. This is x1, y1 plus, I'm going to multiply the t inside. So this is going to be t a1, comma, t a2. And this is equal to x1, y1 plus, so this is equal to, I'm going to add this. This is, guys, by the way, we add the first component x1 plus ta1, comma, y1 now plus ta2. So now this is what? This is x and y. Now I have the vector on the left is equal to the vector on the right. So what does that mean? That means x is equal to that part, which is x1 plus ta1, and y is equal to y1 plus ta2. Those two are called the parametric equations of the line. So these are, the blue ones are the parametric equations of the line. The green one is what we call the vector equation of the line. So we have two definitions about the line. This is all presented in here. Let's look at this equation. Question says, find the vector equation and the parametric equations of the line passing through these 2 points, guys. So let me show you the graph and how do we do this. The first point is 1 and 3, 1, 2, and 3. So here is the first point. This is the x-axis, and this is the y-axis. The second one is 2 and 5. Here is 2 and 5. So this is the second point. What do we have here, guys? We have a line that is passing through those 2 points. Where is this line? This is our line. This is our line L. So far, we know it's passing through the point 1 and 3, 2 and 5. He wants to find the vector equation of the line. What do? We write the vector equation of the line x equal x1, y1 plus t a1 and a2. Now, so what do I need, guys? I always need a point on the line, which I have it. Actually, I'm rich here. I have 2 points, 1, 3 and 2, 5. I can choose whichever I like. Okay, I have 2 points. So let's call this one x1 and this is y1. So x is equal to 1 and 3 plus t times a1 and a2. What is this supposed to be, by the way? a1 and a2, it's supposed to be the vector that is parallel to the line. Where is that vector? Look what I'm going to do, guys. Remember in linear algebra, I'm going to take this vector that starts here and in there. You see that vector? This is a vector. This is a vector on the line, starts at 1, 3 and ends at what? 2, 5. The problem with this vector is not defined from the origin, isn't it? Can I move this one to the origin? Yes. How do we do this? I'm going to call this vector actually A. But this A is starting from what? 1, 3 and ending at 2, 5. There is another way to present A. We can present the vector A as, I don't know if you remember this in linear algebra. So it's x2 minus x1, which is 2 minus 1, comma, 5 minus 3. What is 2 minus 1? It's 1. 5 minus 3 is 2. Look, I'm going to now graph the curve 1 and 2. Here is 1, guys, and here is 2. So this is the point here, 1 and 2. If you connect those two, by the way, this is again A. This vector is the same vector as this, same magnitude, same direction. So now I got the vector A, which is 1 and 2. Instead of being 1, 3 to 2, 5, now it's the new vector 1 and 2. So now this vector, as you notice, it's parallel to what? To the line. So what do we say? So now we can go back and say here that x is equal to 1, 3 plus t times a1, a2 now is the 1 and the 2. 1 and 2. This is the vector equation of the line. A point on the line and a vector parallel to the line. So this is the vector equation of the line. Now, what are the parametric equations of the line? The second part of the question, I need to find the parametric equations of the line. That's easy. What do? We go back to our equation, guys. We replace x with what? With x and y equal to, because this is a vector, starts at the origin and ends at x and y, is equal to 1, 3 plus t, 1 and 2. All I did, I replaced x with x and y. But this is equal to, look, so this is 1 and 3 plus, I'm going to multiply the t inside. So this is t, comma, 2t. I multiply t inside here. And this is equal to, now we're going to add 1 plus t. So it's 1 plus t, comma, 3 plus 2t. This is what we have. So now, guys, x and y is equal to that. And if two vectors are equal, what does that mean? The first component must be equal to the first component. So x is equal to 1 plus t, and y is equal to 3 plus 2t. Those are the parametric equations of the line. It's very easy, huh? So this is how you find the vector and the parametric equations of a line. Same thing happened in 3-dimensional space. It's the same idea. Whether in 2-dimensional space or you are in 3-dimensional space, you always follow the same procedure. Here's an example. Says find the vector and parametric equations of the line passing through this point. So I have a point and it's parallel to the line with vector equation like this, guys. So look what happens here. I'm going to graph. Sorry, we have a 3-dimensional space. All right, so let's make a 3-dimensional space thing. This is the y-axis, this is the z-axis, and this is always the x-axis. There is a line that is passing through the point 1, 2, and 3. By the way, on the x-axis 1, here is 1. Y-axis 2, here is 1, here is 2. So they meet somewhere here. So this is the point 1 and 2. Then on the z-axis, it's a 3. You go to the z-axis 3, 1, 2, and 3. From the y-axis, you go up here. Then you go down. You meet with this point here. So this is the point 1, 2, and 3. What do we do now? we're going to connect, we need to find a line. Now I have a line, red, and this line is passing through the point 1, 2, 3. I'm not going to graph it yet, but it's parallel to the line, the other line. I'm going to make the other line green. This line is passing through the point 0, 1, negative 1. Where is 0, 1, negative 1? X is 0, here it is. Y is 1 here, so this is this one. And Z is negative 1. You go to negative 1 here. So the point is going to be here. So I have another line, green one, is passing through the point 0, 1, negative 1. And it's parallel to this vector. What is this vector? Now we have our vector A is 2, negative 2, and 1. Here is 2 in the x-axis. Here is 2 in the x-axis, 2 in the y-axis. Where do they meet? They will meet somehow here. And then what do we have? They go all the way up to 1 on z equal to 1. So we're going to go to z equal 1. We go here, we meet up. So this is actually here is our vector A. Our line X is passing through this point and parallel to this. So how does our line look like? Look like this, by the way. This is our L2. We have a line that is passing through the point 0, 1, negative 1, which is this point, by the way. And it's parallel to the vector A. The vector A, 2, minus 2, and 1. Let me fix it again. I think we have so many things here. So let me show you 2 and negative 2. Maybe the vector is not very good. So let's, here, 2 and negative 2, x is 2, y is negative 2. My apology, y is negative 2. So where do they meet? They meet somehow here. And then on the z-axis, you go 1 up. Here is up. So you go to the y-axis, you go up. And then they meet somehow in here. So this one, guys, is our vector A. This is our vector A. 2, negative 2, x is 2, y is negative 2, and z is 1. You go to z equal to 1, and then you go down to this point, so they meet here. So this is the vector. So now I have to fix my line. So my line is going to be parallel to this A. So the line is going to go like this. That's our line, the second line. So the second line is parallel to A, to the vector A. Now, my line, L1, I'm going to go to the blue. My line, here's my line, pass through the point 1, 2, 3, and it has to be parallel to this guy. So this is our line, guys. This is our line, L1. I need the vector equation of that. What's the vector equation of that? X is equal to x1, y1, z1, plus t, a1, a2, and a3, which is equal to, we know the line is passing through this point, plus t, and it's parallel to the vector A. Where is A, by the way? This is A. What's A? A is 2, minus 2, and 1. So 2, minus 2, and 1. You see that? This is exactly how the graph will look like for L1 and L2. And this is the vector equation of the line. It's passing through the point 1, 0, 1, so 1, 2, and 3. Here it is. And it's parallel to other line. This other line that I got, the green one, is actually parallel to what? To this A. So this is how it looks like. The green one is our L2. Okay. I need the equation of L1. That's easy. All I need is a line, and I need is a point, sorry. I have a point and a vector parallel to the line. The vector that is parallel to L1 is the vector A. That's it. And this is the equation. What are the parametric equations of the line? We say now here we're going to replace x with x, y, z equal to. Now this is vector equation of the line. To find the parametric equations of the line, we replace x with x, y, z equal to what? 1, 2, 3 plus, let's multiply t inside. So you have 2t minus 2t and t, which is equal to, add, so 1 plus 2t, and then 2 minus 2t and 3 plus t. We add those components. So who's this? This is x, y, z. So what are the parametric equations now? X must be equal to 1 plus 2t, y is equal to 2 minus 2t, and z is equal to 3 plus t. Those are the parametric equations of the line. Which line? The line L1 that is passing through the point 1, 2, 3. And our line L1, actually, it's this line. To be more specific, this is our line L1. Since it is red, this is our line L1. It's passing through the point 1, 2, 3. So this is the point 1, 2, and 3. This is how you solve the question. Now let's learn a little bit of graphing functions in three-dimensional space. How would you graph function like this? To graph this one, we're going to call this one z. So we're going to let z equal x squared plus y squared. Let me show you guys how do we graph this. First, we're going to let z equal 0. So what do we get in this case? We get x squared plus y squared equal to 0. What is this in three-dimensional space? In three-dimensional space, we know that this is circle radius of radius 0, centered at the origin. So this is exactly when z is equal to 0, we are at the origin. All right, so this is a center at the origin. All right, and what's going to happen is going to go up and down because z here is a free, and this will make it circle at radius 0. Now, what else can we do? We can let x equal 0, guys. Only x equals 0. So what do we get? We get z is equal only what? Y squared. So let's graph z equal y squared. I will choose the color red. Z equal y squared. Here is the y-axis. This is the y-axis, and this is the z-axis. Z equal y squared, it's easily seen that this is our graph, right? This is our curve. So we have a parabola. Now, let's go to the next one. Now let y equal 0. This implies that z is equal what? Only x squared. Again, this is parabola between the x-axis and the z-axis. So I have a parabola that goes like this. And it's going to go up. So if you look at the final shape, guys, of this one, it will look like what? Like a cone, or another cone, actually. I would say like a hat, a cap that's going up. Make sense? So this is how it looks like. We can make the behind one like this. So this is how it looks like. This is like a cap. And this is the graph in three-dimensional space. So this is the graph of z equal x squared plus y squared. Keep this in mind. And this is in general how it looks like. This is a nice three-dimensional figure using the computer. How about this one? Same thing, call this one z. We have z equal 9 minus x squared minus y squared. Same thing. Let's start with z equals 0. So what do we have here? We have 0, is equal to 9 minus x squared minus y squared. Bring x squared minus squared to the other side, we get x squared plus y squared is equal to 9. What is this, guys? Let me show you on the graph. What do we get? Again, y-axis, x-axis, and z-axis. In the xy plane, what does this represent? This represents a circle centered at the origin with radius what? 3, isn't it? So this is a circle of radius 3, but it's in the xy plane. So what I'm going to do, I will choose the color of the green since I'm defining everything in green. So if we go here, 1, 2, and 3, and on the left 1, 2, and -3. On the x-axis 1, 2, and 3, and here in the back you have 1, 2, and -3. Connect those. What do we get? This is actually the graph. If you look from the top, what do you see? You will see a full circle, but because we're looking at it from our side, parallel to it, so we see it like an ellipse. Actually, this is not an ellipse. This is exactly a circle. But look in this equation, guys, what do we have? This is a circle of radius 3, all right? And I took z to be what here? 0, right? So in this equation, since we took z to be 0, where is z equal 0? We are in the xy plane, so this is the graph of the function. Now what do we do? Now we're gonna take, let's change the color so we can see what's going on. Color here, let's take the red. Let now x equals 0. So what do we have, guys? We have z is equal to 9 minus y squared. You know very well that this is the parabola z equal y squared, but minus y squared goes down and shifted 9 units up, isn't it? So we're going to say 1, 2, 3, 4, 5, 6, 7, 8, and 9. Here is 9. In this equation, by the way, it's going to be the curve that goes down from both sides. Right? So this is our curve that goes down. Of course, it continues all the way down, and it's going to cross the y-axis at 3. You know why? Because if you let z equal to 0 here in this equation, then what do we get? So we get 9 minus y squared is equal to 0. So y squared is equal to 9. So y is equal plus minus 3. So plus 3 and minus 3, this is the parabola. So the graph of this one is the red one that you see there. Now, let's take the blue one. Change the color. Now let y equal to 0. So what do we get? We get z is equal 9 minus x squared. What is this? The same thing. It's a parabola between z and x. Also, if I take x to be 0, then z is 9. And it's going to go all the way down here to the x equal to 3. And in the back, we're going to go to x equal -3. So now I have this one that goes down. Look at the graph. It's beautiful. Hat, but flipped. It's starting from 9 on the z-axis, and it's going down. And this is how the graph looks like, guys. So from now on, the graph of something like this will look like a paraboloid. This is called a paraboloid. And this is really how it looks like a dome. All righty. Let's look at this one. I have z equal square root of 16 minus x squared minus y squared. To look how this one looks like, guys, I'm going to square both sides, get rid of the square root. Then I'm going to come back to the square root. If I square both sides, so what do we get? We get z squared is equal to 16 minus x squared minus y squared. Bring x squared, y squared to the other side. So what do we get? We get x squared plus y squared plus z squared equal to 16. Remember in calculus 2, we know that this is the graph. You see, if there was no z, it's a circle of radius what? 4. But there is a z now. So how does the graph look like? This is a sphere of radius 4. This is sphere of radius 4. So look, I'm going to graph the sphere here with the different color. So let's choose the green color. Radius 4 means on the y-axis, you're going to go to 4. On the z-axis, you're going to go to 4. Up and 4 down. On the x-axis, you're going to go to 4. 1, 2, 3, 4. You make it smaller here because, see, it's on your side, so you have to be careful here. And in the back, you go to -4. 1, 2, 3, 4. So this is -4. How do we graph the sphere? We're going to go with the y-axis, going to the x-axis at 4. Then you go like that. And here you go like this. This is the thing between x and y. Then between z and y, it's going to be that circle. Oops. Let me fix. It's this is very slippery, the one I'm using here. All right, let's fix that. All right, so I'm going to go slowly now. Here it is, going up and down. Same thing on the x, z. I'm going to go to -4. This is -4, by the way. You go like that, the y-axis. And same thing here, you go like this to the y-axis. So this is not the circle because we're facing it. The last one is between z and x. So on the z, we're going to go like this from z to x equal to 4. And then you go all the way down to -4. And then here, because this is 4, so you go in the back and in the back. So this is how it looks like. We have, as you see here, this is exactly the sphere. But now, guys, if I want to go back, let me go back here and see what's happening. If I want to go back and solve for z. Hello? Right. Here, guys, I'm going to go back and solve for z. So z squared is equal to 16 minus x squared minus what? Y squared. If I take the square root of that, so z is what? Plus minus square root of 16 minus x squared minus y squared. So z have two values. You know which one? The positive one. So z here is equal to positive 16 minus x squared minus y squared. And this one represents, by the way, the upper part of the sphere. It's this part. See, the upper one is this z. So this is z equal square root of 16 minus x squared minus y squared. The other one is going to be the green one, z equal minus 16 minus x squared minus y squared. This is the bottom one, which is the green one, actually. So z equal to minus square root of 16 minus x squared minus y squared represents the lower part of the sphere. So the equation of the upper one is positive root, and the lower one is the negative root of 16 minus x squared minus y squared. So this is the graph of it. It's only the upper one because I need only positive root. So this is the upper one. This graph is kind of, not easy to graph. So we assume that this is the graph of the saddle. Okay. And so keep this in mind. This is the cone. The graph of this one is cone. Why is it a cone? Because if you take z square equal x square plus y square, this start with z equal to 0, guys. So what do we get? We get x square plus y square equal to 0. We know that this is the center here. That's the center here, x, y, and z. Now, let's take x to be 0. So what do we have? So we have z square is equal to y square. Take the square root of both sides. So z is equal to what? Plus minus y. Z equal to y is this one and the bottom one. So z equal plus minus y, and also goes this way and that one. So this one, for example, z equal y, and this one z equal minus y, goes both ways. Now you let y equal to 0. So z square is equal to x square. So z is equal plus minus x. Where is plus minus x? We can say it's the one that goes in the back here, goes down, and the one goes the other direction like this. And if you connect those, you will get the cone. So this is the equation of the cone, guys, in 3-dimensional space. Those are some of the famous graphs you have to keep in mind. All right, now let's proceed. He says, find the vector function that describes the curve C of intersection of these two curves. I have y equal x and z equal to that. I need to find the vector function of the curve that is resulting of the intersection between these two curves, guys, and then graph the resulting intersection curve. So what do we have here, guys? Let's take the big one, which is z equal 4 minus x square minus y square. You remember this z equal to that? Let's go back here. Z minus x square minus y square. Maybe we can find it like this one, right? So it's a paraboloid up and downward. So let's graph this one and see what's going on. Here, let's take z equal to 0. So what do we have? We have, you can move those here. So you have x square plus y square equal 4. So let's graph this one now in 3-dimensional space. Z, y, and x. As you know, this is a circle of radius what? Radius 2. So we're going to go 1, 2, negative 1, negative 2, 1, 2 on the x-axis. In the back, we're going to go negative 1 and negative 2. And then we're going to make the green one. That's the circle in the xy plane. When z is equal to 0, so I have a circle of radius 4 that goes on the ground. Now, if we let x equal to 0, then z is equal 4 minus y squared. Remember, this is a paraboloid that goes all the way to 4. 1, 2, 3, and 4. And it's open downwards because minus y squared. So it's going to go downwards to here. And it's going to go all the way to here. Same thing, if we let y equal to 0. So z is equal 4 minus x squared. Again, this is another paraboloid that goes from here to the x-axis in the back and like this in the back. So this is what we have. It's a paraboloid up and downwards. Now who's going to come, guys? There is now y equal x. So now we're going to take the red one where y is equal x. Where's the graph of this one, by the way? We take y equal x. This is the line of y equal x. But y equal x is what, guys? Y equal x is nothing but a plane, because here there is no z. Here z is a free. So this line is not a line actually, it's a plane that is going to come and cut that paraboloid. So the result of the cut will look like this, guys. It will go like that, and it's going to go down like this. So the result of the cut, here it is. Sorry. This is the result of the cut. So what I'm going to do, I will graph it again here. Here is y equal x. Same color. I will take y equal x. What's going to happen? Now I'm going to go to the green one. Here's the green one. And look at the green one. It goes all the way up to 4, comes down back to x. And this is going to go like that. If you notice here, this is going to go, the green is going to continue like that. And then the curve is going to go all the way up like that and goes a little bit down to this one. So where's the cut, by the way? If you notice here, our curve is exactly this curve. This is the intersection, right? It's going to cut the dome. Because you have this dome, it will be actually cut. We will cut that dome, right? And the result is half of that paraboloid, just half of it. Who is this one? This is our curve C, that result of what? The intersection between the plane y equal x and the paraboloid. So this is the graph of it, guys. So we finished the graph. Now, what else does he want? Let me see. Here it is. The second, he says, find the vector function that describes t. Now, this is a scalar function, so we need to find the vector function of that. So let's go back to our work here. This is y equal x, and this is z. So to present it, guys, in vector form, remember, what do? Let's let x equal to t. If I let x equal to t, guys, what's going to happen to y? How about the y? Then this implies that y is also what? T, isn't it? So what's z? Z is 4 minus x squared, which is t squared, minus y squared, which is what? T squared, which is equal to 4 minus 2t squared. So what's r of t? The vector. Remember, it's x of t I plus y of t j plus z of t k. And x of t, which is x here, I called it t. So this is ti plus y again t plus z is 4 minus 2t squared all k. This is, guys, the vector equation of the line. This is not the vector, sorry. This is the vector. This is how you parameterize the curve. And this is the vector valued function of the curve. So this is the vector function of the curve. So this is the vector function of which curve? The red curve that you see here in the back, or this one here. This is our curve C. If I want to present it in actually parametric form as a vector function, I know that C is the intersection between those two. So I let x equal to t, y. So y is t and z is equal, as you see, 4 minus 2t squared. And this is how you present it as a vector function. Let's look at this one. It says graph the vector equation. This is a vector function or vector equation. How do you graph it, guys? Let's look at what's given here. Remember that r of t is always what? X of t I plus y of t j plus z of t k. So according to the question, x here is a 3 cosine t. Instead of writing x of t every time, let's just write it this way. Y is 3 sine t, and z is equal to 5 only, fixed at 5. So what I'm going to do, guys, from the first two, just in first see what is the situation in the XY plane. I can easily see that if I squared X and I squared Y and I added them, what do I get? Okay, let's square X, guys. Square of this is what? 9 cosine square T plus, this is square Y. So 9 sine square T. I can factor out the 9. So what am I left with? Cosine square T plus sine square T. But we know that sine square plus cosine square is 1. So the answer is 9. So look what we started with, guys. So that means X squared plus Y squared is equal to what? 9. What is this on the graph? Isn't it a circle in the XY plane? Right? Of radius 3. So now we can graph it. So 1, 2, and 3. In the back, you have 1, 2, and -3. On the x-axis, 1, 2, 3. And in the back, you have 1, 2, and -3. What do? We're going to graph that circle. All right, so let's graph that circle in green. Now we have the circle in the XY plane. But don't forget here, we don't have Z, isn't it? Z here so far is free. In this equation, because I took only X and Y, Z is free. So what's going to happen for this Y, guys? Z goes up and down, isn't it? So what's the result of this one? The result of this is going to be what? A cylinder that goes up and down. So I have a cylinder, guys. So if you go all the way up, you can go all the way up and you get a cylinder. Up and down. So this is a cylinder that goes up and down. So what is this, guys? So what is that? This is not a circle. This is what? This is a cylinder of radius 3. Why cylinder? Because the circle here on the XY plane is not just a circle, because Z is free, means I can go up and down. If I go up and down, we get a cylinder. Now, who's going to come? The Z is going to come now. Z is equal to 5, guys. Z equal to 5. What is this? Let's go to 5. Here is 1, 2, 3, 4, and 5. When I say Z equal to 5, we know that X and Y are what? Are 3, right? So X equal to 5. You might think it's a line only, right? No, actually, it's not a line. This line is going to go all directions. It's going to go in this direction, in the XY, and it's fixed at Z equal. So what do we have here? We have a plane, guys. This plane is going to come, and so Z equal to 5 is not a line, it's a plane. The plane is going to come and what? Cut who? Cut the cylinder. What is the result of the cut? The result of the cut is definitely what? This curve, which is this circle. So it's exactly the circle below that moved up. So cylinder goes up, Z equal 5 is a plane. Imagine plane like a card that is going to come and cut that tree that is going up at Z equal to 5. So this is the result of our curve. So this is, guys, our curve. So the graph of this equation is exactly only the blue one. This is the graph. It's just the blue one. This is our R of T. And you can't graph it, as I said, till you change it to what? To standard form. So this is a cylinder of radius 3 that goes up and down. Z equal to 5 is a plane at Z equal 5. So we're going to come and make a plane because X and Y are free, so I can go in all directions, but horizontal to the XY plane. And then the cut will result to what? In that curve. And this is the intersection. And this is the, so R of T is the blue one that you see here in this graph. All right. what are the operations that we can apply into any vector function R of t? I can take the limit of R of t as t goes to a, which is going to be the limit of each component in that vector function, given that all limits exist. For example, okay, another thing we can do, properties of the R of t. If I have a constant, I can always take it out. If I have two vector functions, I can distribute the limit over both of them. Product, I can also distribute the limit. So it's from the same properties of functions. Here is this one, says find the limit of R of t as t approaches 0 from the right of this. So what do I say? I said that the limit of R of t as t approaches 0 from the right is equal to the limit as t approaches 0 from the right of what, guys? Of each component. So we're going to say sine 2t over ti plus limit as t approaches 0 from the right of t minus 2 to the power 5 j plus the limit as t approaches 0 from the right of t ln t k. Alrighty, now let's take them one by one. Let's start with the first one, guys. What's the limit of sine 2t over t as t approaches 0 from the right? This is equal to, from calculus 1, of sine 2t over, I'm going to make this 2t at the bottom 2t. So I multiply the denominator by 2, guys. So what should I do? I should multiply the numerator by 2. So I multiply the numerator and the denominator by 2. Now, this 2, I don't want it inside, so I'm going to take it out. So this is 2, the limit as t approaches 0 from the right of sine 2t over 2t. Remember from calculus 1, the limit of sine theta over theta as theta approaches 0 is 1. So this is 2 times 1, which is 2. So the answer here is 2i. I'm done with the first one. It's 2. Let's go to the second guy. What would be the limit as t approaches 0 from the right of t minus 2 to the power 5? I think this is easy. Just plug 0. So you get 0 minus 2 to the power 5. And this is negative 2 to the power 5. Since the power is odd, so we have minus 2 to the 5. 2 to the 5 is 32, so the answer is negative 32. So I'm going to say here, this is minus 32j. Now let's go to the last one and take another color. From the last one, let's take the purple one. What would be the limit as t approaches 0 from the right of t ln t? Let's plug the 0 first, guys. What do we get? We get 0 times ln 0. You know the graph of ln. As you approach 0 from the right, where is the ln going to? This is ln t. It's going to negative infinity. So this is 0 times negative infinity. Remember, this is one of the what? Undetermined forms, right? So this is one of the undetermined forms. So what do we do in this case? We need to flip one of them. So this is the limit as t approaches 0 from the right. We will keep ln t and bring this one down. So it's going to be what? 1 over t. Now put the 0, guys. If I put at the top, what do I get? I get negative infinity. How about 1 over t? Look at the graph of 1 over t. This is a graph of 1 over t, isn't it? Or 1 over x. As t approaches 0 from the right, where's the function going to? It's going to positive infinity. So this is infinity. And remember, when you have infinity over infinity, what do we apply? We apply L'Hopital rule. So this is the limit as t approaches 0 from the right what do? We differentiate the top. What's the derivative of ln t? It's 1 over t. What's the derivative of 1 over t? Minus 1 over t squared. Let's simplify this. So this is the limit as t approaches 0 from the right of 1 over t times, see, I'm going to change this one to multiplication. So it's going to be what? Minus t squared over 1. I'm flipping it. And this is the limit as t approaches 0 from the right. This t goes with the square. So you're left with negative t. Put the 0. What do you get? You get 0. So the final thing plus 0k. So the final answer is 2i minus 32j. This is the limit of this function, of this vector function. Right? I leave this one for you, just the limit of this one. It's the same solution. Sorry. Now, how do you prove that a vector function is continuous at a point? Remember from the continuity definition, first of all, it has to be defined at this point A. The limit must exist, and number 1 and number 2 must be equal. And in this case, we say that the function is continuous at what? At A. Also, a vector function, where is the function continuous at? Remember from calculus 1, if I need to know where is the function continuous at, what do? We find the domain of the function. All right? And what's the domain of the vector function? It's the intersection of the domain of each component in that function. I will show you in this example. Is this vector function defined at 0? What do, guys? We're going to take r at 0 first. Let's find r of 0. What is this? Okay, so this is the square root of 9 minus 0i plus 3 ln e minus 0j plus sine 0 over 0k. Now this is 3i plus 3 ln e is 1 j plus, now what do I have, guys, in the denominator? I have 0. This part is undefined because the function, so since r of 0 is the k component is not defined, then what do we say? So since this is undefined, therefore r of t is discontinuous at x equals 0, because the last component is not defined as 0 because I have 0 in the denominator. That's it. If the function is not defined as 0, then it's not continuous at 0. Let's look at this question. He wants to know, where is this function continuous at? Give me the interval where it's continuous at. So let's go back to the question. Find the intervals where the following vector functions are continuous at. So let's take one by one. Here's the first one. So what do? We said there is a theorem says that a function is continuous on its domain. So functions are continuous on its domain. So now we're going to find the domain of r of t. Look, how do we find it, guys? We take them one by one. We will start with x of t. X of t is 4 minus t squared. What's the domain of this one? Remember, we say 4 minus t squared must be greater than or equal to 0. Move t squared to the other side. So 4 is greater than t squared. Or I can write this one as t squared less than or equal to 4. Take the square root of that. So that means t is between -2 and 2. So here's the graph, guys, of the first one. Here is 0, -2, and 2. So it's everything between -2 and 2. That's the domain of the first one, including, of course, the -2 and the 2. Now let's take y of t. Ln t minus 1. What's the domain of the logarithmic functions? We know that t minus 1 must be strictly greater than 0. So this implies that t is strictly greater than 1, I'm going to graph this one here. Here is 0, here is 1, excluding the 1. By the way, here is 1, excluding the 1, and it's everything after 1. Here's 1. The last one, z of t, is sine t. What's the domain of sine t? T is all real numbers. So for the last one, it's all real numbers. So here is 0, it's everything. Now, what's common in all of those? Let me show you what's common in all of those. So I'm going to change the color here to red. You will see that 2 here is included in all of them, isn't it? 2 is here, 2 is there, and 2 is there. This region is in all of them. Here is 1. But 1 is not included there, even though it's included here, but it's not included there. So what's common here? The common thing is open at 1, closed at 2. This is the common one. So what's the domain of R of t? It's t belongs to the interval 1 and 2, open at 1, close. It's the intersection between all of this, and this is the domain of our function R of t. Let's look at that one. We need to find the domain of this function. So what do? We take x of t, which is 1 over t. What's the domain here? T is not equal to what? 0. So if you put it here, anything except 0. Anything except 0. Let's go to y of t. T squared. So t belongs to R, all real numbers. Everything, including the 0, all of this. The last one, z of t, is 1 over e to the t. You know the denominator is never 0, so t belongs to R, all real numbers. Everything. What's the intersection between those? What's common in all of them? You see, all of them contain everything. Everything here, all of that is in here. That's in here. Where is the problem at? At 0. 0 is not there. 0 is here. 0 is there, but it's not in the first one. So what's my intersection? It's going to be everything except 0. So it's from negative infinity to 0, union 0 to infinity, because 0 is not common in all of them. So the domain of R of t is what? Is t belongs to negative infinity to 0, union 0 to infinity, which implies that R of t is continuous on the same thing, on t that belongs negative infinity to 0, union 0 to infinity. And I should say the same thing in the back one. This is the domain, which implies that R of t is continuous on t belongs to 1, open, 2, closed. Because we're talking about continuity, not only the domain. All right, how do you differentiate a vector function? It's the derivative of every component in the vector valued function. You differentiate everything, g, g prime, h, h prime, r, r prime. Let's look at this. This is R of t, guys. Question number 1, I don't have to solve it. What's the derivative? It's a derivative of every component. The derivative of tangent is secant square. Here it is. The derivative of 5 to the t, remember, it's 5 to the t ln 5 from calculus 1. The derivative of ln t is 1 over t. That's it. What's the derivative of the second one? The derivative of e to the t square is e to the t square itself times the derivative of the power, which is what? Which is 2t. Sine inverse t, it's 1 over square root of 1 minus t squared. This formula is known from calculus 1, j, plus The derivative of tangent inverse is 1 over 1 plus t squared k, and you are done. This is how you differentiate the vector function. It's the derivative of every component in that vector. Let's look now at this question. Graph the curve C, whose position is given by r of t. So I have this curve now, r of t represents a graph, which is cosine 2ti plus sine t. We're going to graph it first, from 0 to 2 pi only. Okay. Then graph the tangent lines, this one and this one. So let's start the graphing, guys. This is what was given. I was given the vector function, and I need to graph it. So let's graph this one first. Forget about r prime at 0, the graph of that. Let's start with this one. Remember, you cannot graph a vector function till you change it to the standard form. Who is this? That's x. So x here is cosine 2t, and y is sine t. Cosine 2t, this is double angle, and this is one angle. They don't match. I have to have the same thing. Both of them must be a function of t only. But we know that cosine 2t, what is this equal to? One of the identities of this one is 1 minus 2 sine squared t. Remember this one? So I changed the cosine to a function of sine. So look at this. So now x is 1 minus 2 sine squared t. But what's sine t? Sine t is y, isn't it? So I can write this one is what? 1 minus 2. And instead of sine, I'm going to say what? Y squared. So look what we have, guys. So from this one, we conclude that x is equal to 1 minus 2 y squared. Done. I changed it from vector function to what? To a standard function. How do we graph this? Let's graph that thing on two-dimensional space. You know, if you take y to be 0, then x is what? Is 1. Here is 1. If you take x to be 0, you take x to be 0, so what do we get? We get 1 minus 2y squared is equal to 0. So 2y squared is equal to 1. So that means y squared is equal to half. So y is plus minus square root of half. Square root of half, I think it's 0.71, around something like this. So here's point on the x. This is what? This is the x-intercept. And on the y-intercept, if this is 1 and this is negative 1, 0.7 is somewhere here, negative 0.7 is somewhere here. We know this is the graph of this parabola that goes like this. Right? This is the graph of the function. This is the graph of x equal 1 minus 2y squared. I'm done with the graph. See, very easy. From 0 to 2 pi, this is how you graph the function. Now, for t equal to 0, what's x equal to? X is equal cosine 2 times 0, and cosine 0 is what? 1. So when t is equal to 0, x is 1. How about y? Y is sine 0, which is 0. So what do we have from here? X is 1 and y is 0. X is 1, y is 0. Here it is. You see that? Now, let's go to the extreme, which is 2 pi. When t is equal to 2 pi, then x is what? X is equal cosine 4 pi, isn't it? And cosine 4 pi is the same thing as cosine 2 pi is the same thing as 0, which is 1. And y is equal sine 4 pi. And this is again what? 0. So we're going back to the same point. So this is exactly how it goes. All right. So this is the value of the function. So they really have this intersection point, and then at the end, it continues, extends to infinity. Now, what do I need to find, guys? He wants to find what is r prime at 0. Okay, let's find r prime of t, guys, in general. To graph r prime, so we're going to differentiate. Remember, how do you differentiate? So differentiate the derivative of cosine. What's the derivative of cosine? It's negative sine 2t times the derivative of 2t, which is 2. Here it is. And this is I. Plus the derivative of sine is cosine t, j. This is r prime of t in general. What's r prime at 0? It's negative 2 times sine 0i plus cosine 0j, which is equal to, we know that this is 0, so it's 0i plus 1j. And I can write this one as 0, 1, by the way. It's the vector 0, 1. Where is the vector 0, 1? I'm going to make it in red. The vector 0, 1, here is the point, by the way, 0 and 1. So this is our vector. This is our vector 0 and 1. This is supposed to be what? R prime at 0, isn't it? But we're not supposed to have it here. Remember, when you differentiate, this is supposed to be what? A tangent. So r prime of 0 must be a tangent vector to the curve at what point? This is the question. So now what I'm going to do, I will go back and find what is r at 0, guys. Go back to the question and replace t with 0. So this is cosine 0i plus sine 0j. Cosine 0 is 1, so this is 1i plus 0j, and this can be written as 1 and 0. Where is the point 1 and 0? This is the point, by the way, 1 and 0. So this red one, which is r prime at 0, is not supposed to be here. It is supposed to be what? Tangent to this curve at this point. So I'm going to move it here. So actually now, this is the correct one. This is r prime at 0. It is supposed to be what? The vector tangent to the curve. Which curve? This is our r of t. Where at the point y0, 1? Because when I put it in the curve, I get the point 1 and 0. So now this is r prime of 0, guys. And now I'm done with the first curve. R prime of 0 is finished. Let's do the pi over 6. We have space for r pi over 6. Let me then give a space for r prime at pi over 6. All right, so I'm going to make here another space. Blank one. All right, so now let's graph r prime at pi over 6. We're going to follow the same thing here. Now, let's go with different color. Green. R prime at pi over 6 is what? Let's go to r prime. This is r prime, so it's negative 2 sine 2 times pi over 6 I plus cosine pi over 6 j. And this is equal to negative 2 sine pi over 3 I plus cosine pi over 6 j. And this is equal to negative 2 sine pi over 3, which is 60, is root 3 over 2 I plus cosine pi over 6 is actually also root 3 over 2 j. Cosine 30 is root 3 over 2. Now this one goes with that one. So I'm left with what? Minus root 3 I plus root 3 over 2 j. And this can be written like this, minus root 3 and root 3 over 2 like this without j, sorry. Now let's go to the calculator. Probably we can get an estimate of what is the cube root of this one. All right. So the cube root of 3, so the cube root of 3 is 1.44. So this is negative 1.44. Let's say 1.4. Okay. And the cube root of 3, so the cube root of 3 is equal to this divided by 2. This will give me 0.7, comma, 0.7, almost 0.7. So let's plug this one now on the curve, guys, the green one. So what do we have? Minus 1.4 is almost here. So this is negative 1. And here, negative 2. Negative minus 1.4 is somewhere here, guys. So this is minus 1.4. And 0.7 almost here. So they're going to meet at this point. So this is the point, guys, which is minus 1.4 and 0.7. I will connect this with what? With an arrow. Who's this now? This is r prime at pi over 6. But it's not supposed to be here. Where should it be, guys? It should be somewhere on the curve. So what do I do now? I'm going to find r at pi over 6. Where is r? This is our function r in this. So this is cosine 2 times pi over 6i plus sine pi over 6j. This one's cosine pi over 3. So this is cosine pi over 3 plus sine pi over 6j. This is I and this is j. Cosine this is half I plus also this is half j. So I'm going to put it like this, half and half. Where is half? This is half, guys. Where is half here? This is half. Where do they meet? They meet somewhere here, roughly. Here is the point. So this is the point, half and half. This is r at pi over 6, which is half and half. What do we do here, guys? We're going to take this curve, the green one, and graph it here. There you are. This is, by the way, r prime at pi over 6. Just put it up there, and this is the graph of r prime of pi over 6. You see, it has to be tangent to the curve. And this is the graph of the r prime of pi over 6. All right. Let's do this one, guys. Same thing. Graph the curve C with this position. R of t is 2 cosine plus 6 sine t. And then graph r prime pi over 6. So let's take the question itself. Now, this one, as you know, we can't graph without before we change it to the standard form. This is x and this is y. So x here is equal to cosine t. And y is equal 6 sine t. If I square both sides, we're not going to get 1, by the way. It's not going to work. So from the first one, I'm going to divide by 2. So x over 2 is what? Is cosine t. From the second one, y over 6 is sine t. Now, we are going to add those two. So x squared over 4 plus y squared over 36. If I add those, square and add, sorry. So what do we get? We get cosine squared t plus sine squared 2. What did I do? I squared this, then I added to the square of that. So that means I'm going to square this and add it to the square of that. But we know this is equal to what? 1. So what do we have now, guys? We have x squared over 4 plus y squared over 36 is equal to 1. Do you know what's this? This is the ellipse. This is a graph of an ellipse. How do you graph it? Look at this. I'm going to let y equal 0. So what do we get? So we get x squared over 4 is equal to 1. which implies that x squared is equal to 4, which implies that x is equal plus minus 2. So let's go to the graph of the function. So x at 2 and minus 2. Here is 1, here is 2, here is -1, and here is -2. We have an ellipse here. All right. Now we're not finished yet. Now where do we go to? We go to x. Now let x equal to 0. So I have y squared over 36 is equal to 1. So that means y squared is equal to 36, which implies that y is equal to what? Plus minus 6. Let's go here and see how far can we go. 1, 2, 3, 4, 5, 6. 1, 2. Extend that thing here down. And then go to the green one. 2, 3, 4, 5, and 6. So this is -6 and this is 6. Now we're going to make the graph, guys. The ellipse. Then we're going to go up to 2. And then continue from 2 all the way to 6. This is the graph of our vector function. It's nothing but the ellipse. See how easy it is? Now, what do we need to do? We need to find this graph, that one. Okay, what's r prime of t first? The derivative of cosine is sine, so this is -2 sine ti, and the derivative of this sine is cosine, so 6 cosine tj. This is r prime of t. So r prime at pi over 6 is -2 sine pi over 6i plus 6 cosine pi over 6j. And this is -2. Sine 30 is half I plus 6. This is square root of 3 over 2 j. And this is -1i plus 3 root 3 j. And this can be written as -1 and 3 root 3. So let me see as a vector, what's the maximum of 3 root 3? So square root, cube root of 3 is 1.4, okay, times 3. So this is almost 4.3. So this is -1 and 4.3. This is r prime at pi over 6. So where is this one? -1, here it is. 4 is here. 4.3 is somewhere here. So they will come and they will meet somewhere here. So now, instead of making it with green, I'm going to make the color here, change it to red. I hope I can easily connect. Sorry about that, but this is our line. Who is this? This is r prime at pi over 6. But what's the problem with this guy? The problem with this guy, he's not on the curve. It has to be on the curve, tangent to the curve. But at what point? At the point what? R at pi over 6. So let's go back to the question. So this is 2 cosine pi over 6 I plus 6 sine pi over 6 j. And this is equal to 2 root 3 over 2 I plus 6 times half j. And this is root 3 and what? And 3. Root 3, I think, is around 1.7, and this is 3. 1.7 is somewhere here, and 3 is here. So they will meet somehow here. So this is root 3 and 3. This is the point on the curve. What I'm going to do now, from this point, we will make the same vector. So now this is r prime at pi over 6. This is the graph of it. Got it? This is how you graph the function. So I just moved it to be tangent to the curve at the point, with a point which is root 3 and 3. All right, guys. So I hope this one is useful, and this is how you graph the function, vector function, and the tangents to the vector functions. How do you differentiate a vector function? You differentiate every component in the vector function. Whether we differentiate it once, so you differentiate each one once. So if I differentiate once, so it's a derivative of once. Twice, here is twice. N times, you differentiate n times. Here's, for example, r of t is given like that. So what's the derivative of this? This is a product of two functions. So how do you differentiate that? Here it is. It's the first times, okay, so it's the derivative of the first, which is 1, times the second, plus the first, which is t, times derivative of cosine, which is minus sine. So this is all I. The derivative of sine is cosine. The derivative of t is 1. The derivative of cosine is minus sine. So this is the first derivative, and then you do the second derivative, and this is how you do it. So no need to work on this one. I leave this one for you to find the second derivative. All right. Let's suppose that r is a function of s, and s is a function of t. Remember chain rule? Then how do I differentiate the vector function with respect to t? I can't, because r is a function of s. How do I differentiate with t? From the first chain theorem, it's dr over ds times ds over dt, guys. This is how we differentiate the function. Chain rule for the vector function. Let's look at this example. R is a function of s, which is tangent 5si secant sj plus ln s squared k. And s is equal to t4. He wants to find dr over dt. Dr over dt is impossible to find because r is a function of s. So what do? We use chain rule. So this is dr over ds, because r is a function of s, times ds over dt, because s is a function of t. S is a function of t. All right, let's go to dr over ds, guys. Here is r. This differential with respect to s. What's the derivative of tangent? The derivative of tangent is secant square 5s times the derivative of the 5s with respect to s, which is what? 5. So you put 5 here, and then I. Plus, what's the derivative of secant? It's secant tan. So this is secant s tangent s j, plus what's the derivative of ln s square? The derivative of ln s square is s square goes down, and who goes down? Up. The derivative of s square, which is 2s. Okay, this is dr over ds multiplied now by ds over dt. What's the derivative of s with respect to t? It's 4t cubed. So now let's multiply. So this is 5 times 4, sorry, this is 20 secant square 5s times what? Times t cubed. So I'm gonna fix the 20 here, put it in a nice way. So this is 20 t cubed times secant square 5si plus multiply here 4t cubed secant s tangent s j, and here we know that this s goes with the square. So what do we have? Plus 8t cubed over s k, and this is equal to, we're not done yet, 20t secant square 5s. What's s, by the way? S is t to the 4. So this is 5t to the 4 I plus 4t to the 3 secant s, which is t to the 4, tangent s, which is t to the 4 j, plus 8. Now S is t to the 4, and there is t to the q on the top, so this is s over 8 over t. Okay, this is, guys, the final derivative with respect to t. You see, I was asking about dr over dt. The answer has to be a function of t only, and we got it as a function of t. Same thing here, dr over dt is dr over ds times ds over dt. dr over ds, the derivative, the exponential function is the exponential function itself times the derivative of the power I, plus 3 to the s square, it's a 3 to the s square times ln 3 times the derivative of s square, which is 2s j, plus the derivative of cosecant is minus cosecant to cotangent. So this is minus cosecant s square cotangent s square times the derivative of s square, which is 2s, and this is k. Now, all of this, guys, is just dr over ds times ds over dt. What's the derivative of root t? You know, this t is t to the half. The derivative of that, we know, if I want to differentiate this, it's what? Half t to the minus half, which is 1 over 2 t to the half, and this is 1 over 2 root t. So this is 1 over 2 square root of t, which is equal to 2. S is what? Root t. So here is root t. E to the s square. If I square this, what do I get? I get t I plus 3. S square is t ln 3 times 2 times s, which is what? Root t j, minus 2 root t cosecant s square is t tangent, so cotangent s square is t k. All of this is multiplied 1 over root t. So what's going to happen, guys? 2 root t is going to go with this one. So I have e to the ti plus, same thing, this is going to go with that. And I have 3 to the t ln 3j. And the same thing here, 2t will go with this one. I left with plus, sorry, minus cosecant t cotangent t, all of that k. This is, guys, dr over dt. How do you differentiate the sum of two vector functions? You can distribute the derivative of both of them. If I have two vector functions, what's the derivative of that? You know, product rule, first times derivative of the second plus the second times derivative of the first. What's the derivative of the dot product between two functions, two vector functions? Same thing, it's the first times derivative times dot, not times, dot, the second plus the second dot the first. And the derivative of this is exactly r of t cross r prime plus r prime cross r2. So product rule is applied for the product, but instead of here, it's a multiplication, so we do multiplication. Here dot, so we do dot. Cross, we do cross here. All right, so let's do one of those two, guys. Let me do the first part A. He wants to find d over dt of r of t dot u of t. R of t is here, by the way. I'm going to copy it down. So it's 6t plus 8i plus 4t squared plus 2t minus 3j plus 5tk. That's r of t dot u of t. What's u of t here? Here it is. So you have t squared minus 3i plus 2t plus 4j plus t cubed minus 3t k, and we close. There is the long way, which is the formula. I just gave it to you guys. And there is the fast way. What am I going to say? So this is d over dt. Remember, how do you do dot product between two vectors? We multiply the I component with the I component. So what do I have? 6t plus 8 is multiplied by t cubed minus 3. Then what? Plus, remember, because the dot product is a scalar, there's no more vector. This one times this one. So 4t squared plus 2t minus 3 multiplied by 2t plus 4. Plus the last one, component of this, which is 5t multiplied by t cubed minus 3t. And this is the result of the dot product between these two vectors, guys, which is equal to d over dt of what? Let's multiply. 6t times t cubed is 6t to the 4. Then 6t times minus 3 is minus 18t. Then 8 times this is 8t cubed, and 8 times negative 3 is minus 24. Plus 4t squared times 2t is 8t cubed. 4t times 4 is plus 16t squared. 2t times 2t is 4t squared. 2t times 4 is plus 8t. Minus 3 times 2t is minus 6t. Minus 3 times 4 is minus 12. Last one here, 5t times t cubed is 5t to the 4. 5t times this is minus 15t squared, and we close, which is equal to d over dt. Let's simplify, guys. Let's look at this. 6t4 and 5t4 is 11t to the 4. So those are done. Let's go to t cubed. 8t cubed and 8t cubed is 16t cubed. So this one and this one are going to go away. So plus 16t cubed. Now let's look at the t now. So a t squared. 16t squared and 4t squared is 20t squared. 20t squared minus 15t squared is 5t squared. So all of those are gone. So we said plus 5t squared. Now let's look at the t. Minus 18t minus 6t is minus 24t. So minus 24t. So I'm going to cancel this. I'm going to cancel. So I mean, there is 8t. Minus, okay, so minus 18 plus 8 is minus 10. Minus 10 and minus 6 is minus 16. So this is minus 16t. So now this also goes away. Now minus 24 and minus 12 is minus 36, and we close. Now we differentiate, guys. So what do we get? It's 11 times 4 times t cubed. The derivative of t4 is 4t cubed plus 16 times 3 times t squared plus this is 10t minus 16, and this is equal to 44t cubed. Then 3 times 16, this is 30, 48 plus 48t squared plus 10t minus 16. Alrighty, so this is how you do the derivative of the dot product. How about the derivative of the cross product between these two? It's going to be lengthy. So to do this one, I would suggest to do the cross product first. U cross U prime. What is this? Remember in linear algebra? So those are vectors. So put I, J, and K. U is this one, which is t squared minus 3. and 2t plus 4, and here t cube minus 3t. This is u. Now, u prime, the derivative of that is 2t. The derivative of that is 2. The derivative of that is 3t squared minus 3. How do you find the determinant of that? I'm going to take the first two columns and put them outside. T squared minus 3 and 2t. Then I'm going to take the j, which is 2t plus 4 and 2. I don't know if you know the procedure. We do diagonally. So this is equal to this times that, which is 2t plus 4 multiplied by 3t squared minus 3i, plus, now we go this way, which is 2t multiplied by t cubed minus 3t and j, plus this way, 2t squared minus 6k. Now we say minus, we go backwards this way. Minus what? 2t times that, so 2t times 2t plus 4i, minus, we go this way. 2 times that, that's easy. This is 2t cube minus 6t j. Finally, so this is, sorry, my apology. When we went back, this is k, then I. Now let's go the last one here. So what do we have? Minus 3t squared minus 3 times t squared minus 3k. So this one is j. Now let's simplify it. Let's look at the I. So here, this is 2, no, so this is 6t cube, this times that, then minus 6t, then plus 12t squared minus 12i. But I'm going to go and see where is I also. I is here too. So this is minus 2t cube, minus with minus is a plus 6t, all of that I. Now let's go to the j, guys. This one is what? Plus 2t4 minus 6t squared. And there is also j here. So what is this? 3t squared times t squared is 6. So minus 3t to the 4. And then this one times the 3 is minus a 3 and minus is a plus 9t squared. Then negative 3 times t squared is minus 3t squared, and there is a minus, so plus 3t squared. Then minus a 3 times minus a 3 is minus 9, and there is a plus 9, and there is a minus, so we say plus 9. All of this is j. Plus, let's look at the k, 2t squared minus 6. Where is k? Also here, 2t times 2t is minus 4t squared, and 2t times this is 8t minus 8t, all of that k. Let's simplify now. 6t cubed minus 2t cubed is 4t cubed. Now plus 12t squared minus 60 plus 60, they cancel, and minus 12i plus 2t to the 4 minus 3t to the 4 is minus t to the 4. T cube, there is no t cube. Minus 6t squared, and 9t square is a 3t square, and 3t square is actually 3t square, right? Because this 6 minus 6 plus 9 is a 3, and 3 is 6t square. What's left here? Just 9. J. Plus the last one is 2t square minus 4t square is minus 2t square. Then minus 8t, there is nothing with it. And then minus 6k. This is u cross u prime. What's the derivative of that? D over dt, guys, of u cross u prime is equal to what? Now we differentiate this. What's the derivative of that? 12t square plus 24t all I plus derivative of that is minus 4t cube plus 12t j. The last one plus minus 4t minus 8k. This is the derivative of the cross product. How do you integrate the vector function? You actually integrate each component in the vector function. Let's integrate this one, guys. What's the integration of that one? I need to integrate from 0 to 4 of this one. So what do we say? It's equal to the integration of 2t plus 1 square root of that dti plus integration from 0 to 4. There is a minus, so let's put the minus here. Then square root of t dt j, and the last one plus the integration from 0 to 4 of sine pi t dt k. So I distributed the integral over all of those. Now on the side, I'm going to do one by one, by the way. So what would be the integration of 2t plus 1 under the square root dt? To do this one, guys, you let u equal the inside. And then you differentiate. Du is equal to what? 2 dt. In the question, I have only dt. So dt, so du over 2 is dt. We do this one by substitution. So what is this equal to 2? This is u, square root of u. Then dt is du over 2. The half goes out, and then you have the integration of u to the half. What's the integration of u to the half? It's u to the 3/2 times 2 over 3. You should divide, but it goes. So this one goes with that. And the answer is u, which is what? U to the 3/2 over 3. But what's u? It's the square root of that. So it's a 2t plus 1 to the power half, because this is u, right? It's a square root. Sorry. Okay, so this is to the 3/2 over 3. So this, the first one is 3t plus 1 over 3. This is all to the power 3/2 from 0 to 4. I minus. This is what? This is t to the half, isn't it? What's the integration of t to the half? It's t to the 3 over 2 times 2 over 3. And this is from 0 to 4. Plus, what's the integration of sine pi t? You know, to integrate sine pi t, you let u. So now what's the integration of sine pi t dt? Let u equal pi t. So du equal to pi dt, isn't it? Divide by pi, so du over pi is equal to dt. So what is this equal to? This is equal to the integration of sine u. Then dt is what? Du over pi. Take the pi out. What's the integration of cosine? It's negative cosine u. But this is minus cosine. What's u now? U is pi t over pi. So the answer for this one is minus, let's say plus here, minus cosine pi t over pi, and this is from 0 to 4. Now what do we do, guys? We plug the 4 now first. If I put 4 here, what do I get? Get 12 plus 1 is 15. So this is 15 to the 3/2 over 3 minus, we plug the 0 now. If I put the 0, I get 1 to the 3/2, which is what? 1 over 3, so minus 1 over 3. Minus, put the 4, you get 2, then 4 to the 3/2 over 3, then put the 0, minus 0. We put 0 for the t, it goes away. Plus, put the 4, it's going to be minus cosine 4 pi over pi, minus and minus becomes plus cosine 0 over pi. Now, we said we put the 4, 4 times the 3 is 12. 13, my apologies. So this is 13, not 15. This is the 13. So the answer is 13 to the power 3/2 over 3 minus 1/3. Here, by the way, 4 to the 3/2. What's 4 to the 3/2? We know that 4 is 2 square to the power 3/2. So 2 goes with 2, you get 2 cube, which is 8. So this one is 8 times 2 is 16 over 3. Cosine 4 pi is the same thing as cosine 0, which is 1. So we're going to say minus 1 over pi, plus with plus is plus, cosine 0 is 1 over pi. This one cancels this one. So we have 13 to the 3/2 over 3. Minus 1/3 and minus this is minus 17 over 3. And this is the final answer without using a calculator. Now, how do we find the length of the vector function? You know, the vector function is a curve and it has a beginning and end. So this is our vector function from t here, from here to here. How can we find the length of this one? This is our r of t, vector function. How do I find the length? The length is the integration from a to b of the square root of the derivative of each component square dt. Alrighty? So let's look at question 1 and question 2. Let's do the first one, guys. So what do I need to find for number 1? I need to find s. What's s equal to? It's the integration, since it is from 0 to pi. So this is from 0 to pi of what? The square root of the derivative of the first one square, which is 1, plus the derivative of this guy, it's the first t times derivative of cosine, which is negative sine t, so minus, plus the derivative of the first is 1 times cosine t, all square, plus this one the same thing, the first times derivative of the second, which is cosine t, plus the derivative of the first, which is 1 times sine t, all square, and then we say dt. And this is equal to the integration from 0 to pi of the square root of the following. This is 1 plus, this is square this one, guys. It's the square of the first, which is t square sine square t. Then the first times the second times 2. So it's going to be minus 2t sine t cosine t. Then plus the square of the last, plus cosine square t. Then let's go to the second one. So the first is plus, so let's make the square root big one, plus the square of the first, it's t square cosine square t. Then the first times the second times 2, which is plus 2 t cosine t sine t. Then the square of the last, which is sine square t, and all of that dt. So what do we get? We get the 0 to pi of the integration of 1. Now, look at this one, t square sine square and t square cosine square. I'm going to take t square out. So what do I have? I have sine square t plus cosine square t. Then minus 2 cosine plus this one goes away. So what am I left with? Cosine square plus sine square plus cosine square t plus sine square t, and then dt. But we know that this is 1, and we know that this is 1. So what is this equal to? The integration from 0 to pi of the square root. This is 1, and this is 1, is 2 plus t square dt. Now we have to integrate this one. From calculus 2, remember, this is like what? Square root of 2. This is the integration from 0 to pi of the square root of a square root of 2 square plus t square dt. Remember this integration by trig substitution. Here, a is equal root 2. So we let t equal a, which is root 2 tangent theta. If you remember this one. So dt is equal to square root secant square theta d theta. So let's continue. So this is equal to the integration from 0 to pi of the square root of the square root of 2 square. Again, bring it back to 2 plus t square. If you square this one, you get 2 tangent square theta. dt is this, which is root 2 secant square theta d theta, which is equal to integration 0 to pi. Here I can factor the 2 out, isn't it? So it goes out. So root 2 out. What am I left with? With 1 plus tangent square theta times root 2 secant square theta d theta. But this root 2 times this root 2 is 2. So this is equal to 2 integration from 0 to pi. 1 plus tangent square is secant square. So this is the square root of secant square theta times secant square theta d theta, which is equal to 2 integration from 0 to pi of secant cube theta d theta. Now, how do you integrate secant cube theta? Let me put it here on the side. Okay. The integration, let's take that space here. So this turns out to be a long question. So what's the integration of secant cube theta d theta? This is equal to the integration. I will split it to secant theta and secant square theta d theta. Then I'm going to do it by parts. U and dv. Who's u, by the way? dv is the one that is integrable. This is integrable. So I'm going to take this one as secant square theta d theta. So what's u? Secant theta. What do? We find du. What's the derivative of secant? It's secant theta tangent theta. How about this one? V is the integration of secant square is tangent theta. So the integration of that, guys, by parts, it's u times v, which is secant theta tangent theta minus the integration of this times that. If I multiply this one, what do we get? We'll get secant tangent square, secant theta tangent square theta d theta, which is equal to secant theta tangent theta minus, by the way, this tangent square is secant square minus 1. So this is secant theta times secant square theta minus 1 d theta, which is equal to secant theta tangent theta Now let's open this. So this is minus the integration of secant square theta, d theta, minus with minus is plus the integration of secant theta, d theta. So look what happened. The integration of secant cube is equal to, it's coming in the answer. Bring this one to the other side. So what do I have? So 2 integration of secant cube theta d theta is nothing but what? Secant theta tangent theta plus, do you know what's integration of secant from calculus 1? This is ln secant theta plus tangent theta. So guess what? The integration of secant cube is that. Divide by 2. So we can say that the integration of 2 this, so this is equal to 2 integration to, so 2 secant cube is nothing but, so the answer is secant theta tangent theta plus ln secant theta plus tangent theta, and this is from 0 to pi. But don't forget the question was 0 to pi for t. So I have to bring secant theta and tangent theta to its origin. All right, so what is actually here now? What did we assume here? We assumed that t is equal to that. Now t is equal square root 2 tangent theta. So tangent theta is t over square root of 2. Here's the graph. Here's theta. Tangent is the opposite over this one. If I square this one, so the answer is 4. Sorry, it's 2 plus t squared. So this is equal to secant theta is the reciprocal of the sine, which is what? The sine is the opposite. Sorry, secant is the reciprocal of the cosine. Okay, so this is for the secant, it's supposed to be the reciprocal of root 2 over that. So it's going to be square root of 2 plus t squared over what? Over root 2. It's the hypotenuse over what? Over the adjacent. Tangent theta, it's the opposite over the adjacent. So it's t over root 2. Tangent theta is opposite over adjacent. Plus ln secant again, it's a square root of 2 plus t squared over square root of 2 plus tangent theta, it's t over square root of 2. Close this one, and this is from 0 to pi. Now this with this is 2, so this is equal to, we're going to replace t with pi. So what do we have? Square root of t 2 plus pi square times t, which is pi, divided by root 2 times root 2 is 2, plus ln square root of 2 plus pi square over root 2 plus pi over root 2. That's when you plug the pi. If I plug the 0, what do we get here? We get 0. And here we put 0, so it's going to be root 2 over 2, which is going to be 1. So this is minus ln root 2 over root 2 plus 0. But root 2 over 2 is 1, so this is all 0. So I'm left with this answer. This is the answer of this integration, guys. Let's do this one, the second one, 2. S is equal to the integration from 0 to 1 now, from 0 to 1, of the square root of the derivative of each one square. The derivative of that is minus 2 sine t all square plus the derivative of that is 2 cosine 2 square plus the derivative of the last one is 1 dt, 1 of course square. And this is equal to the square root from 0 to 1 of the square root of, if you square this, we get 4 sine square t plus 4 cosine square t plus 1 dt. And this is equal to the integration from 0 to 1 of the square root. From the first two terms, guys, I'm going to factor 4. So what am I left with? Sine square t plus cosine square t plus 1. And this is equal to the integration from 0 to 1. This is 4. We know that this is 1. So this is 4 plus 1, which is the square root of 5 dt. We can take the square root of 5. So this is the integration of this one. And this is the square root of 5. The integration of dt is t from 0 to 1. And this is equal to square root of 2. Put the 1 minus the 0. And the final answer is square root of 5. This is the result of this integration, only square root of 5. And with this one, guys, we conclude the whole section. It was a heavy one. Now, after we know how to graph three-dimensional space, after we understood what is the vector function, how do you differentiate it, how do you integrate it, how do you find the limits, and how do you graph it actually, now we're going to go to the second part, more applications on the vector function. So what we did here today is we converted standard functions to vector functions. And then we applied graphing to them, limits, etc., integration, and all operations on the vector functions. Okay, guys, I hope you enjoyed it. We see you in the next video. You guys have a good day.